Next, let's move on to the fourth chapter, which is continuous time Fourier transform. Okay, right. So we write down for a continuous time signal. Okay, for a continuous time signal x of t, continuous time Fourier transform. Okay, we call CT continuous time Fourier transform as CTFT. Okay, for a continuous time signal x of t, CTFT is defined as, okay, CTFT is defined as what? X of j omega is equal to integral minus infinity to infinity x of t multiplied with e power minus j omega t dt. So let us call this equation as 1. So if you look at this equation little bit carefully, you can easily see that this is nothing but the dot product of the signal x of t with e power j omega t. Okay, so that is the dot product of the signal x of t with e power j omega t. Okay, so definitely what does this mean? It implies that, okay, so this implies, okay, for example, I take x of, let's say, j1, which is nothing but dot product between x of t with e power j1 times t, means frequency of the signal is 1 radians per second. So let's assume that this fellow is 10 power minus 2. Okay, so this implies what? This implies the signal, which signal? The signal e power jt, because e power j times 1 into t is e power jt, is less present. Okay, why? It is 10 power minus 2, and hence we say that e power jt is less present in x of t, is less present in x of t. With the same argument, let us say if let us say x of j10, okay, x of j10, which is equal to a dot product of the signal with e power j times 10t, and if this fellow is like 10 square, what does this mean here? This implies, what does this mean? So this implies the signal, which signal? E power j10t is largely present. Okay, so is largely present in x of t. Okay, in x of t. So what does, so this is what? This is a Fourier transform of the signal at 10. So this implies what? So Fourier transform will quantify the presence of the frequency e power j10t or e power jt and so on. Okay, so what does this imply here? So this implies e power, so not e power, so this implies the frequency of 1 radians per second. Correct? The frequency of 1 radian per second is less, okay, is less in x of t. Okay, so that's what it says. Why 10 power minus 2? Similarly, what does this imply? So this implies frequency of how many radians per second? 10 radians per second is more. Okay, so is more in x of t. Okay, so that signal is more in x of t. So the Fourier transform, what it tells? It tells which frequency is present in the signal and how much it is present in the signal. Okay, so this, that is, okay, so that is the Fourier transform or the CTFT x of j omega quantifies. Okay, so that fellow will quantifies the presence of which frequency? The presence of frequency omega in the signal x of t. So the presence of the frequency omega in the signal x of t. So Fourier transform will tell us all that information. Okay, yes. So before we go into the details, if you look at the equation x of j omega, which is integral minus infinity to infinity x of t power minus j omega t dt. So this fellow will tell us the frequency component that is present in the signal, and hence we call this equation as what? Analysis equation. Okay, so we call this equation as analysis equation. Okay, so similarly, given Fourier transform, how do you find the signal x of t? Okay, so then we call it as the inverse Fourier transform. Okay, so that we call it as what? Inverse CTFT. So inverse CTFT is what? Is given by, so you have to get back the signal x of t. So what is that? X of t is equal to 1 by 2 pi integral minus infinity to infinity x of j omega multiplied with e power plus j omega t dt, sorry, e power j omega t d omega. So this we call it as what? This we call it as inverse Fourier transform. So clearly, given Fourier transform x of j omega, you are getting back the signal x of t. But if you look at this equation little bit carefully, what does it say here? This is again looking like what? Linear combination of complex exponentials. But what linear combination? It is continuous linear combination. Okay, so this can be seen as okay, continuous linear combination of continuous linear, why continuous? Because there is integral. So continuous linear combination of complex exponentials. Okay, continuous linear combination of complex exponentials. Okay, so this we call it as what? Because you are getting back the signal x of t, we call this equation as what? Synthesis equation. Okay, so we call this equation as what? Synthesis equation. Okay, let us give numbers. Let us call this fellow equation 2, and the actual signal, yeah, we already called it 1. Okay, yes, so in that way we get we have seen both analysis and synthesis equation. So what will analysis equation tell? Analysis equation will tell you to find out which frequency component is present in the signal. Similarly, synthesis equation will tell you how do you get back the signal x of t from the Fourier transform. Okay, right. So what happens now? Let us come back to the Fourier transform. So we write down that in general, correct? So in general, we'll talk first about Fourier transform. Okay, in general, the Fourier transform x of j omega is complex. Correct? So because this fellow is complex, it can be written as, okay, so it can be written as, okay, that Fourier transform can be written as what? X of j omega is equal to what? Real part, which is xr of j omega plus j times the imaginary part, which is xi of j omega. This is one way of representing the Fourier transform. Why? Because it is complex. We can write in terms of real part plus j into imaginary part, or we can write this also in terms of polar form, which is we write it as modulus of x of j omega multiplied with e power j times angle of x of j omega. Okay, so this is writing in regular complex form, real part plus j into imaginary part, and polar form is modulus of x of j omega into e power j angle of x of j omega. Where how are these fellows related here? Where modulus of x of j omega is equal to how much? Xr square of j omega plus xi square of j omega, okay, whole power half. So whole power half. And similarly, what is angle of x of j omega? Angle of x of j omega would be tan inverse of imaginary part, which is xi of j omega divided by real part, which is xr of j omega. So whichever is convenient we can write. So we can write either in terms of real part plus j into imaginary part, or in polar form, which is mod x of j omega multiplied with e power j angle of x of j omega. Okay, and where mod x of j omega is given by xr square of j omega plus xi square of j omega whole power half, and angle of x of j omega would be tan inverse of xi of j omega divided by xr of j omega. Okay.